I want to talk about some of the stuff we talked about in the last day and a half. Do some of the story problems that were in the PDF yesterday, and then get into some of the last questions of that PDF and wrap up this section. But the first thing I want to show you is this idea that we've been talking about with the sine function and its relationship to the sine inverse function, and kind of understanding and developing that kind of comfort level with what our calculator is going to be providing us, or any technology will be providing us. First thing I have up there is just your triangle in the first quadrant here. I've got a hypotenuse of 1, a 60-degree angle, so then you see across on that 60, you get your root 3 over 2, and then your adjacent side there, you get your 1 over 2. So that's a 30, 60, 90 triangle, right? Okay. Now, maybe we're more comfortable just from, just because of our division, to make that R value, if we can make it grow to, get straight, or exactly at 2. There we go. Make that R value grow to 2, and now you're seeing that when I deal with the sine of 60, it is the opposite value, that's a radical 3 right there, divided by the hypotenuse, which is a 2. So I do get that radical 3 over 2. Does that make sense? Okay. But the idea is that no matter how big that R is, you see that the adjacent and the opposite side have to adjust to it. Okay. So if I take 1.29904 divided by 0.75, you're seeing that it still evaluates to radical 3 over 2. There's an equation inside this phrase right here that's making it go to radical 3 over 2. If I see here, just kind of want to prove it to you. Okay, there we've got you see where it says opposite divided by j. Opposite side divided by j is the hypotenuse of that 1.5. So it is giving me evaluating that radical 3 over 2, or the 0.866 here. I've got so really what's going on here, I've got two different things being calculated, but they evaluate out to be the same thing. One, I've got the function for sine, and it's inserting into the sine function, just like your calculator would, where you see that theta, it's plugging in that 60 right now, okay? And it's getting this 0.866 back. This is dividing that number by that number, and it's getting the radical 3 over 2. But those two things equate, right? And it might be a little bit easier to see them equate when they're not an exact radical 3 over 2, okay? So if I get that opposite side and that hypotenuse, we would see that those two things do equate. Is that okay with everybody? Okay. So what I'm trying to show you here is that I've got two calculations up there, both of them referencing different values. One of them referencing an angle, the other one referencing the sides divided by one another, and they're the same number, right? So that's where we get the argument that sine is the same thing, or equates to the opposite divided by the hypotenuse. Is that all right? Okay. What I think is important, though, for us to understand is how that then relates back to maybe our sine inverse. Okay, if I take 60 degrees, okay, and I'm dealing with the sine inverse, so I'm going to just draw in something here real quick. So I'm going to make that blue, okay? Because what the sine inverse is going to do is it's only ever going to provide you measurements that come out of that blue region, okay? If we go back to what we talked about yesterday, the range for the sine inverse is between negative 90 degrees and positive 90 degrees, right? Or in radians, it's negative pi over 2 to positive pi over 2. So that, negative pi over 2, you guys would maybe think about, if I asked you to draw out an angle of negative pi over 2, you would go there, right? That would be negative pi over 2. If I asked you to draw an angle out that's pi over 2, it would be there. So you see that we're only talking about those two quadrants when we go sine inverse, okay? Here's the thing. There is a situation where if I look at this right now and I say I want to find the sine inverse. Okay, now the sine inverse, we put a number in here, right? We put a ratio in there. Let's say of 0.86603, which is the root 3 over 2, and our calculator is going to spit back 60 degrees, right? Would you guys all agree with that? This ratio right now, that ratio is a positive number, correct? Is there anywhere else in the quadrant plane, or sorry, coordinate plane, that the ratio for sine is also positive? What other quadrant is sine positive? It's positive in the second quadrant, right? So I should be able to, drill that number in your head right now, 0.866 or radical 3 over 2. I should be also able to find the same sine value over here in the second quadrant, right? We see that 0.866, and we see the radical 3 over 2, but this angle, this 120 degree angle, is no longer in this blue stuff, right? So what I'm trying to show you here is our calculator, our technology, because how it's referencing the inverse function, will never spit back that 120, even though that we know the sine of 120 is 0.866. Is that all right, everybody? So I think maybe yesterday I might have written something down that looked like, I just want to get rid of some stuff here. I think I wrote like the sine of 60 degrees is going to give you root 3 over 2. And then if we do sine inverse of root 3 over 2, that's going to give you 60 degrees back, right? That's what we use on our calculator, okay? And those two pieces of information there are the inverse functions of one another. You see at the input of 60 in the black expression becomes the output of 60 in the blue one, right? And the output of radical 3 over 2 in the black expression or black equation becomes the input in the blue one, right? So the inputs and outputs have switched, which means the x's and y's switch, which means those are the inverses, right? Okay. But we also know from our investigation of the coordinate plane and these triangles with angles that are bigger than 90 degrees, we also know that sine of 120 is equal to root 3 over 2. Okay. However, sine inverse of root 3 over 2 is going to give you back what? It's going to give you back 60. Okay? So those two things are not inverses right now, right? With the idea of x's and y's switching. So what I want you to realize is that even though this is true, and it is needed and useful, okay, and it's going to be a lot of times the answer that we are asked for, the second part of the answer that we're asked for, this is the only information that your calculator is ever going to spit back to you. All right? We also have to know that 120 also has an output of radical 3 over 2. Is that okay? I think in the past when I taught this, maybe we didn't talk about that enough, and people are always getting do a question, there's two answers, and they get one answer, okay? They don't even show the work to get the second one, or even know if the second one existed, okay? You need to realize, based on directions a lot of times, that there could be a second answer that we're interested in, okay? Same thing happens with cosine. However, cosine is going to, on your calculator, cosine is only going to give you things in those two quadrants, okay? So let's say I'm dealing with the cosine. Now these numbers don't make sense now, but let's see, I'm going to put cosine of theta in here. Okay, so text. All right, so this is the cosine, so this would be the adjacent divided by the hypotenuse, right? And that obviously makes sense when our hypotenuse is 1. But as we start to deal with our calculator, if I type in cosine of 49 degrees, this is the number that's going to spit back, right? 0.65606. But if I type in cosine inverse of 0.65606, what's going to get spit back? 49, right? Okay. But would you guys agree that that ratio right there is positive? Is there another quadrant that the cosine is positive? Yeah. Okay. So we have the idea, that's the adjacent side for that triangle right there. Adjacent divided by hypotenuse. Hypotenuse being 1 again. We get 0.65606 divided by 1. Again, that same number, right? But that angle, okay, that angle is what we see to be right in there. It's 311 degrees. Okay? So the cosine of 49 is equal to 0.65606, which is also equal to the cosine of 311. However, your calculator, when I type in cosine inverse of 0.65606, is only ever going to give me back to 49. We have to do the additional work, have additional understanding to know that 311 will give me back the same ratio. Is that all right? Okay. That's something we're going to keep working with, keep dealing with. It won't go away. So my hopes are is that we learn that, understand that, develop a comfort level with it as soon as possible, just to alleviate, I think, a lot of the stress that occurs when you're going through WebAssign. You're like, I'm getting 50% of these all right. Okay, what's wrong with my work? If we can learn that now, get that understood now, we won't have that issue. All right, so why do we need these inverse functions? We've dealt with this kind of stuff in Algebra 2. We did it in geometry quite a bit. We get these story problems that we want to address, and usually they're asking now for these angles. So just reading this through, it says a 40-foot ladder leans against a building, so that's a terrible building. So there's our building. We've got a 40-foot ladder. Base of the ladder is 6 feet from the base of the building. So they're saying that this is the ground. Obviously, there's the base of my ladder. There's the base of my building. That's 6 feet. Is everybody okay with that? Okay. Here's my right angle. We had to make that assumption that the building is 90 degrees to the ground. It says, what is the angle formed by the ladder in the building? Well, that angle between the ladder and the building would be this angle up here, right? We have the ability to find that theta. What side is this in regards to theta? Opposite. And which one's this? Hypotenuse. Which trig ratio uses opposite and hypotenuse? Sine. So I know I'm going to use sine. And I say sine of theta is equal to opposite over hypotenuse. If you want to reduce that, you can. You don't need to because you can grab your calculator anyways. But I want to solve for theta, right? Right now, this is solve for sine of theta. I can't do anything without getting that thing out of the argument. I need to pull that theta out. It's locked inside that sine function. It's like, for instance, if I had an equation like root x is equal to like 12. I need to do something to get that x out, right? It's locked underneath that radical. Well, what is the inverse of root x? Square. So I square that side and then square this side, right? And that's going to unlock that x. Same idea here. You have to be able to unlock that theta, and you use, square root of x and x squared are inverses, right? So to get this theta out, we're going to use the same concept. We need inverses. So I'm going to inverse the left-hand side. So I take sine inverse. Okay. Now, just kind of thinking here, let's just prove something to you. If I take sine inverse of sine of, now I'm just going to use a first quadrant angle, let's say 30 degrees. What do you think I'm going to get back? 30 degrees. Okay. If I tried 80 degrees, what do you think I'm going to get back? 80. If I tried, see what negative 80 looks like. What do I get back? Negative 80, right? What about if I tried 190? Now there is an issue, right? I don't get 190 back. Why? Anybody know? Yeah, sine inverse is only between negative 90 and 90, right? Those are the outputs, okay? So we're getting an issue with that negative 10. So when we're doing this, the idea is that there are specific outputs that we have to have, or inputs here, that we have to have because of the sine inverse function. So there's some domain ideas going on here. But generally speaking, we're going to be okay here and say sine inverse of sine is always going to get back to us theta, right? Now, if I took sine inverse of the left-hand side, I got to do the same thing over on the right-hand side. And I now get sine inverse of 6/40. We're going to type that in our calculator. Sine inverse of 6 divided by 40, 8.62 degrees. 8.63 degrees. Round it right. Is that something we can do? All right. Now, most of the time, you guys probably aren't by hand going to write all that algebra out, right? You're probably not going to write sine inverse of sine theta equals sine inverse of 6/40. Most of your probably should say, okay, you've got my picture. I know I'm looking for an angle, so I'm going to go straight to my calculator, sine inverse 6/40, right? Okay. Perfect, fine, nothing wrong with that. But I do want you to understand why we're typing it in that way. Where that comes from, that it is an equation that we're doing to get that expression typing on our calculator. Knowing that as well, I think it's going to help us maybe in the coming examples, example 6 and 7, when we get those, or get to those here in a little bit. The next question is the same thing. Says the lighthouse is located on an island that is 2 miles off a straight shoreline. It's expressed the angle formed by the beam of light in the shoreline in terms of the distance d in the figure. So the only thing here that's happening is in the last one, we had 2 dimensions. We had, 6 and 40 in the last question. Here, that d value is going to vary. It's a variable, right? It's going to change. Because as the light kind of rotates in that lighthouse, that distance changes, right? So what we're kind of maybe trying to build to is a series of questions that you might see in a calculus class called related rates. And we can talk about how, based on how that distance changes, how does theta change? So we're going to actually develop an equation here for finding that theta based on whatever d is. And it's really not that hard. If I'm trying to figure out what theta is, how would you find theta? What side is this over here? Opposite, and what side is this? Adjacent. So you would say tangent of theta is equal to opposite over adjacent, right? Okay. So now if I wanted to solve for theta, I wanted to develop an equation that tells me what theta is based on this length here of d, we would take the tan inverse of both sides, right? So tan inverse. And the reason we can do this, we're making the assumption because tan inverse goes between Your output values that you're going to get are between negative pi over 2 and pi over 2 again, just like the sine. And that's the assumption when we work with this. We're going to get those types of angles. So we get theta back when we take tan inverse of tangent. Now, tan inverse of the right-hand side would be just 2 divided by d, right? So now I have a function, I have an equation that is going to give me that theta and show how that theta changes based on how d changes, right? Okay. It's really the same question as before, but that second number is a variable now, and it's going to be able to change. And I think maybe the only reason they give us this type of question is because there you have to use that blue equation, right? You have to have that understanding of the tangent inverse, I think, to and how that relates to the tangent to come up with that red equation. Is this something we can do? Okay. Let's get down to these. These are things, and they're just trying to set up some kind of preliminary ideas and procedures, essentially, that we're going to need pretty much beyond this section for the rest of the year. Okay, it's going to be something that you do on a very regular basis in regards to finding answers for these questions, because of the idea of what our calculator can provide us and what we then need to do in addition to that answer that the calculator gives us. Okay, so right now I'm going to say, so look, when we're looking at sine of theta equals 0.4, but look at the directions. It says find theta, so that's between 0 and 180. It says find all angles theta between 0 and 180. So that, if I read that, that might kind of elicit a thought that there's going to be maybe more than one answer, right? How many answers can our calculator give us? Just one. Okay? So we've got to do a little bit of work here, and I think it's always a good idea to draw a picture. Okay? The first thing to do here is, sine of theta. This is not a really nice number. Okay? Sine of theta is equal to 0.4. I'm going to take the sine inverse of this side, because I want to know what theta is, right? So take sine inverse of that side. I'm going to take the sine inverse of the 0.4 side. On the left-hand side, I get theta. On the right-hand side, I get sine inverse of 0.4. It's also kind of intelligent to think about what our input values for sine inverse are allowed to be. They're allowed to be between negative 1 and 1, right? And that's what we've got. 0.4 is between there. That's my domain for this thing. So it's going to be okay. I'm going to get an output. But my output is going to be between negative 90 degrees and positive 90 degrees, right? So I'm going to type that in my calculator. Sine inverse of 0.4 gives me back that angle, right? 23.57. Okay. And this is where people struggle. This is what I was trying to get to earlier, is that they think that's the only answer. They type that in, they write that down, whatever, submit their work, and they miss 50% of the question. Okay? Because of this idea. If I know that sine of theta was 0.4, I know sine of theta was 0.4. Here's my picture. 0.4 is a positive number, right? So sine is positive in that quadrant, correct? Okay. So the answer my calculator is giving me back is theta right here, because it can only give me back stuff in those two quadrants, right? Sine inverse can only give me back the stuff in the red quadrants here, but we know that the sine is also positive in the second quadrant, so we got to do some work to find the second quadrant angle. Okay. The 0.4 is, a couple different ways of viewing this. You could say, that's 0.4, and the hypotenuse is 1 of that triangle, right? Or you could say maybe that's 2, and that's 5, because that still evaluates to 0.4, right? Okay. But if that's 0.4, and that's a positive 0.4, isn't there a triangle over here where that could be 1, and that could be 0.4. And if I divide those numbers, they're still opposite in hypotenuse, right? A positive divided by a positive is still positive, correct? Okay. So that angle, which is that green angle, is the one we're kind of looking for here. Okay, that's what I'm going to answer the question. But what would that angle there be? Either numerically or in comparison to what is over here. This angle is theta, right? Okay. This is 0.4, this is 1. That's a right angle. That's a right angle. You can go through the work. You can find that distance there and that distance there, right? Okay. Those distances, guys, are going to be the same, aren't they? Do you have two triangles that are congruent here? By side, side, side. So that means that this angle here is also theta, isn't it? This blue angle here? So I'm going to draw it this way. I'm going to go if that's 0.4, that's 1. Theta, we know over in the first quadrant is 23.57, right? That means this angle here in this triangle is 23.57. But if I want this green angle, that's the theta I'm looking for. Okay? How do I find that angle? How do I find that green angle? 180 minus 23.57 will give me my other angle. So I'm going to type that in. 180 minus that thing, you get 156.42. So theta here, the thetas that we're looking for are 23.57 and 156.42. Those are the two angles that we should get 0.4 back when we run them through the sine function. And they're both between 0 and 180, right? So we satisfy the directions. And if we check this, you should always be able to check these guys. Right? Especially, a lot of people struggle, even if they know that this second angle exists, they struggle in regards to how they find it. So it's always a good idea to say, is my first one right? Type in, because we use sine inverse, right, to do all this. Go back, because this is just a normal equation. So once you find your answer, you should be able to plug your answer back in the equation and get a true statement, right? So I'm going to type in my answer of 23. Hit enter. Gives me 0.4, right? So I know that is a true value for theta. I'm going to do the exact same thing then for that number there. The number my calculator did not provide me. It's the number that I had to do a little bit of work with. And if I hit enter, it gives me 0.4, right? Now, it's a lot of zeros and a 3 because that 4218215 is rounded. Does that make sense? Okay. But, I'm in the ball. If I would have even got like 0.3999999 repeating, or, this one, 0.40 repeating with a 3 at the end. Our calculator is doing some rounding here, but we can make the argument that it's 0.4. Does that make sense? Okay. So that tells me that those two angles are the angles that we're looking for that satisfy that condition, that equation. Is that all right? Okay. Hopefully you see it. That second one is not obvious, recalling things from our calculator. Let's do the second one here. It's kind of the same picture because the 0.4. If I do cosine of 0.4, cosine, again, now that number is positive, right? So cosine can be positive first quadrant, correct? So cosine is adjacent, so that'd be 0.4, right? And that'd be 1. Or I think in the last class, guys, I did 2 here and 5 there. Is that still 0.4? Yeah, okay. You could put 4 and 10. So any numbers in there, as long as their ratio turns out to be 0.4. And if that's theta, okay, we should be able to use the cosine inverse key. Cosine inverse of theta is equal to cosine inverse of 0.4. That should give me, It's cosine inverse of cosine theta. That should give me theta is equal to cosine inverse of 0.4, right? Type that in, see what we get. That's 66.42. Okay, so that is, again, that first angle in that first quadrant, right? That's theta that I've shown in that first quadrant. But let's think about where cosine is also positive. All students take calculus, right? Cosine's positive in the first quadrant because of all, but it's positive in the fourth quadrant because cosine is adjacent divided by hypotenuse. And if I look in the fourth quadrant, I look at my triangle in the fourth quadrant. Is your adjacent side still the positive x-axis? So it's still positive 0.4, right? Your hypotenuse is always positive, so you still have a positive divided by a positive, right? Are those two triangles congruent? So what does that tell you this angle right here is going to be? It's at 66.42 as well, right? Okay. Now you've got some ways you could write this. Because if I start with my initial right at the positive x-axis and I go that way, and I'm tracing out this theta now, and we know it was, I don't know why I put a bar there, it's just theta. I know it's 66.42 degrees, but it's going downward, it's going clockwise. What do I call that? Yeah, negative 66.42, right? I don't need that extra, the 6, not a 0.6 there. So negative 66.42. Type that in your calculator real quick. Cosine of negative that number, okay, should give me back what when I hit enter? 0.4. Okay? Now think about this. Right now, we have two answers. Theta is 66.42 or theta is negative 66.42. Is that between, remember the original question said we want to look between 0 and 180 as our interval, right? Is that in between 0 and 180? No. Okay? Now, another thing to think about is that we don't necessarily like dealing with negative angles, right? So maybe you find out, yeah, it's negative 66.42, but we don't like that. So we're going to take that negative 66.42 number, and what can I add to that to make it positive? What can I add? Because that angle of negative 66.42 shouldn't it be the same as that angle right there? So what can I add to it? 360. Okay, so these two things are coterminal. So if I take cosine of that angle, cosine 293, hit enter, what should it give me? 0.4. And it does, right? But based on my directions, what is my only answer here? 66.42. Even though I've got those other angles that do give me 0.4 back, okay? And, you know, I could take this number here, and could I add 360 to it, add 360 to it, add 360 to it, so I found a coterminal angle that went around 3 more times, hit enter, still give me 0.4, right? So what I want you to know is that there's an infinite number of angles that are going to give me back 0.4, right? If they keep adding, multiply, keep adding those coterminal angles. But the homework assignments, the test questions, they're going to ask you for 1 or 2 of them. Does that make sense? And they're usually going to ask for 2 because the second one that you're looking for is the one that you got to do a little bit of legwork to find. Your calculator's not going to do it for you. Okay? That being said, let's get down to this stuff down here. Okay, example set. That's really the same idea. And it plays off a little bit of our algebra from the first semester of the year when we had, you guys remember dealing with composite functions? Okay. we've got the cosine being kind of the outermost function here, and then sine inverse being the innermost function, right? When we deal with composite functions, remember evaluating them, we want to go inside out, okay? So I'm just going to write a generic phrase here for us to really understand what we're doing. We got the cosine as the outside function, and then we've got the sine inverse as the inside function. Now, my question is, sine inverse, whenever you take the inverse, what is this argument? What object is this? Is it an angle or is it a ratio? It's a ratio. Okay? So if I'm working inside out, okay, I have sine inverse of a ratio. If I type that in on my calculator, or maybe special right triangles or whatever, when I evaluate a sine inverse of a ratio, what is that red stuff going to spit back to me? It's going to spit back an angle, right? And now, once I evaluate that, I've got an angle here, but I've still got the cosine out in front now, right? What's the cosine of an angle? If I evaluate a cosine of an angle, what's that going to spit back to me as a final answer? A ratio. So that's what we're looking for. That's what we're going to develop here with this question, is a ratio. Okay? And you can, with a lot of these, maybe use your calculator to get an idea of what your answer is going to look like. Okay? Now this one's really nice because just the numbers work out, and I type in cosine sine inverse of, what is it? Is it 2/5? 3/5? Should give me 0.8 back. And it does. Now usually they're going to ask you for a fraction. So 0.8 as a fraction is 4/5. Okay? But when you're doing problems like this, that 3 and 5, not always going to be really nice numbers like 3 and 5, right? So they might not give back something like really nice like 0.8. It might give something back with a radical in it. And your calculator won't do that. It'll always put it at the decimal, right? So sometimes when they ask for a fraction an exact value, using your calculator isn't going to get that exact value. You'll get the decimal approximation of it, right? So we're still got to be able to do this by hand. So I want to show you how you do this by hand. But your calculator should allow you to always check yourself. Sine inverse of 3/5. You know that's a ratio, right? Okay? It's a ratio of sides, and the sides are opposite in hypotenuse, right? And what kind of number is 3/5? Is it positive or is it negative? It's positive. Okay, so sine is positive in what quadrants? First and second. Okay? Now, sine inverse, the only time that I'm going to get a number back from sine inverse is when it's between negative 90 and positive 90, right? So does it kind of make sense that this angle theta that we're looking for has to be in the first quadrant? Even though sine is positive in the second quadrant, sine inverse is going to be kind of undefined in the second quadrant. Okay? We're not going to get a value back from that. So we won't work in first quadrant here. The ratio of opposite side to hypotenuse is 3:5, correct? Okay. So what this does, when I say sine inverse of 3/5, it is actually giving me this picture for that angle right there, right? If I typed in sine inverse of 3/5, it's going to tell me what that theta is. Now, I'm not really big on what that theta is at the moment. We'll talk about it here in a little bit. But I'm just going to say sine inverse of 3/5 provides that theta. When I look at this picture, now that I have this picture, can I determine what cosine of that angle is? Cosine of theta? Doesn't this Pythagorean theorem says that has to be 4, doesn't it? Okay. So what is cosine? Cosine is adjacent divided by hypotenuse. Do you see where we get our 0.8 then? Doing it this way with the calculator, when we went sine inverse of 3/5, That's the theta that our picture is showing, right? I just wrote it as theta, but it's actually a 36.869 number. Okay? Well, if I find cosine of that number, right, should give me 0.8 back. Okay? But again, we don't like to deal with that 36.86 number because it's not a nice number. And a lot of times it's going to be a really ugly number, so let's just call it theta. Draw the picture. You always have two sides to your right triangle. Find the third side, and then evaluate the trig function, sine, cosine, or tangent appropriately. They could ask, there's a lot of different questions they could ask here now. Could they do, tangent of sine inverse of 3/5? Sine inverse of 3/5 is going to give you the exact same picture, right? Tangent is opposite over adjacent, correct? Okay, so what should I get? 0.75, correct? If I did this, if I just type in tangent sine inverse of 3/5, let's see if we get that 0.75 back, and we do. Okay, so even though it's just the cosine and sine here, this number here could be, or that function could be cosine, could be tangent, could be secant, cosecant, it could be sine again. Okay, kind of redundant though if it's sine, isn't it? Okay, because sine inverse is going to give you this picture here, right? And the sine of that theta then is opposite of hypotenuse, which is going to be 3/5. Using then that's the inverse idea that they undo each other, correct? Okay, so that's what we're looking for in questions like that. And in that assignment 5.4, there's a couple of those. But there's also a couple like this, and these are usually what people don't really care for too much. But it's the exact same idea. It's the exact same problem. We've got the sine of cosine inverse of x. What I want you to remember is that we've got sine, cosine inverse of a ratio, right? And I think if you can visualize that, you understand what the input values are for these two functions. Either the input from the sine function is being an angle, or the input from the cosine inverse function being a ratio. Knowing those things is going to help you understand really what you're supposed to do here. Because they're saying, so we get this one here, they're saying our ratio is x. Well, a ratio is a comparison of two numbers through division. That's what its definition is. We only got one number there, right? What's the understood number here? What are we dividing by? Doesn't this say that? Is that all right with everybody? It's just a formatting thing, a notation thing that really throws people off, and they don't know what to do here. But if you can do that, now go back to the last question. The last question, there were specific values there, right? Now there's arbitrary. So let's just say, drawing our picture now, okay? Working our way from the inside out. So cosine inverse of x over 1. Cosine inverse is a ratio of sine lengths. It's positive, right? We're going to make the assumption that it's positive. If they want it to be negative, they probably put negative x there, right? And when I give you a variable, the understanding is, that variable could be positive, could be negative. Let's make the assumption it's positive here. So let's say that's a positive number. We know the hypotenuse is always a positive number, right? So this thing has to occur either in the first quadrant or the fourth quadrant, correct? That's where cosine's positive. But cosine inverse has to be from what quadrant? What are the outputs that the cosine inverse comes from? Or develops? They're 0 to 180. They're in the first and second quadrant. Okay? So that tells me essentially that we're looking again at an angle here in the first quadrant. Okay? That's the theta that we're interested in. That's the theta that this thing is going to provide. Okay? Well, cosine is adjacent divided by hypotenuse, right? Okay? You have two sides of a right triangle there. And with two sides of the right triangle, you always find a third side. All right, so we can say x squared plus, let's just let this be our unknown, I'll call it b, plus b squared is equal to 1 squared, right? Would you agree that b squared is equal to 1 minus x squared? And then b would equal root 1 minus x squared, right? Now it would be a plus or minus. What quadrant are we in? First, and that distance right there in the first quadrant is positive. Is that okay? So that's the exact same thing we went through in the last question to find when we gave the 3 and the 4, sorry, the 3 and the 5. We went through the Pythagorean theorem to find the 4 for the adjacent side, right? Now we're going to do the Pythagorean theorem to find that argument for the opposite. So now, this thing, like, again, that thing gave me this statement. Provided this triangle, provided that angle. So I'm really now asking, what is sine of that theta? Well, sine is opposite over hypotenuse, correct? Opposite over hypotenuse. Opposite would be root 1 minus x squared. And hypotenuse is 1. So that's what we're looking for. Okay. Now, they have to write this. Don't really worry too much about it. They have to write that because my cosine, my domain values for cosine inverse have to be between -1 and 1, right? Anything outside that, if you type in cosine inverse on your calculator and type in a number like so if I type in cosine inverse of like 5, that's outside 1 and -1, right? And enter. So domain enter. Okay, so they have to provide that restriction. Don't want to worry about too much stuff. What if they ask me this one here? What if they ask me that? Okay? Well, we've already found cosine inverse, right? Cosine inverse, the inside, gives me this picture. What would be the tangent for this picture? That's theta. Tangent is that divided by that, right? So it'd be root 1 minus x squared on the rest. Okay? What's nice about that is now you know trigonometric functions based off one unknown variable, right? Okay? You can do a lot of this kind of stuff in calculus and getting like arbitrary values for side lengths and seeing how that impacts other ideas, other concepts. It's a good skill to have. But what is important about understanding that question is that it's the same thing as example 7. But when you just see that x, remember that's a ratio, it's a fraction, x over 1. All right, and that usually throws people off if they don't pay attention to that. You have the 5.